Right. Last time we had our first interaction with NumPy's argument functions, and in this lecture, we'll continue the trend. We'll examine the argument where function and discuss its syntax, its outputs, and some of its applications. Before all of that, though, it's time we discuss where the argument part of the names of these functions originates. Somewhat surprisingly, the first such usage of the term comes from astronomy. Centuries ago, astronomers would look at a planet's position in the night sky and use tables to determine where it sits in space. These tables would be filled based on the angle at which the celestial objects reflect light, and those very same angles were called arguments. The name literally translates to that which elucidates something else. So, you can think of arguments as coordinates in space, which perfectly translates to how indices work in indie arrays. Therefore, functions that return coordinates within an array are called argument functions. All right, after this quick origin story about argument functions, let's get coding. Once again, we assume you've already imported NumPy, so we're jumping straight into loading the dataset and displaying its contents on screen. Splendid! Then, just like the argument sort, we'll first call the function, look at the output, and then analyze it. So, we write np.argwhere, and in the parentheses, we add the dataset variable, lending, company, data, numeric. The output is a 2D array of integers that appears to hold repeating values in the first column and consecutive non-repeating values in the second column. This is a bit odd looking at first, but don't get discouraged. The given result will make perfect sense in a few minutes when we explain what the function does and what each column represents. All right, so the argument where function goes over the entire indie array and checks whether the individual elements satisfy a given condition. Since it's an argument function, the outputs are the indices for all the individual elements where the condition is met. More precisely, the first column represents the row index, and the second one, the column index. Therefore, we can look at the rows of the output as the coordinates for each value from the original array which satisfies the given condition. However, what condition are we referring to? We haven't specified any condition so far. Well, the default condition is to check for values different from 0. If we look at the array displayed in the previous cell, we'll see none of the first 3, or last 3 individual elements of the array are 0. Hence, their coordinates should appear in the output. This explains why 0, 0, 0, 1, and 0, 2 all appear at the beginning of the argument array. The exact same thing can be said about the last 3 rows of the argument array as well. They represent these elements from the original array, and as we can see, none of them equals 0. Knowing this, the output makes much more sense, since it states those 6 values are non-zero. All right. On the contrary, if we're interested in finding where zeros appear in the array, we can set the condition equal to false and run the cell. This time, the output contains only 2 rows, which suggests there are only 2 zeros in the dataset. To test if this is correct, we can display the row with index 116. According to the argument array, there should be a 0 in position with index 4, which is the 5th position. The output verifies this as well. We can quickly check the row with index 430 and see that there is another 0 in index position 3. And that means that the second row of the argument array is also accurate. Great! Now that we know that the function works as intended, let's quickly display the dataset once more and dive into why it's so handy. The argument where function is very useful because the condition doesn't have to be equal to 0 or not equal to 0. It could be any mathematical condition. A comparative one, like greater than 1,000 or smaller than 1,000. It can even be a more complex one, like is even, which we express as divisible by 2 with no remainder, with the help of the percentage sign. In case you've forgotten, the percentage sign indicates remainder after division in Python. Essentially, we can use this function to separate only the elements that interest us and examine just them. The process is very similar to the filtering related to conditional slicing. The main difference being that slicing gives us the actual values, while argument where returns their coordinates within the array. Therefore, if in your analysis you need a new array that will contain the values you can use in computations directly, you should opt for filtering. However, if you only need the indices of these values to obtain other information about your dataset before you proceed with the next step of your analytic work, then using the arguments where function must be of choice. Fantastic! By the way, unlike argument sort, argument where does not have an equivalent method. That means we will get an attribute error if we try to call it. You see? Before we wrap this lecture up, we want to highlight one of the ways argument where can be combined with another function for a very useful collaboration. We want to quickly examine the synergy between NumPy's isInAn and argument where. To show this, we need a dataset with missing values. If we call the isInAn function on our current dataset and then add the sum method at the end, we'll see that there are 0 missing values here. Hence, we need to load another dataset. Earlier in the course, we used the lending company numeric inan.csv for a similar task. So we can do the same here. Just paste the code where we load our current dataset and make the necessary changes to the name of the variable, the file while importing, as well as the delimiter. Of course, make sure to change the name of the variable we're displaying on the next row to lending company data numeric inan and run the cell. We clearly see a missing value in the first column, so this dataset is suitable for the task at hand. Now that we have everything set up, let's call the np isInAn function and plug in our newly created dataset variable as an argument. As we can expect, the output is an array that tells us whether we have a missing value for each entry of the array. However, it doesn't give us all the places where we get such values, since the default output only shows the first 3 and last 3 rows. Hence, we won't be able to tell if there are missing values anywhere in between. Here is where argument where comes into play. In a new cell, pass the expression we worked with as an argument of the argwhere function. In theory, since false is equivalent to 0, this should give us the coordinates for all the missing elements of the array. Let's see if that's the case. We get a 2D array as the output with the coordinates of many points. To see if these correspond to missing values indeed, in a new cell, we can display a few of the values with the suggested coordinates. Therefore, we can check the row with index 11. According to the argument where output, the value with index 3, also known as position 4, should be missing. After running the cell, we see that this is accurate. We can check a few other rows like 152 or 175 just to be sure, but the outputs always support our claim. Therefore, we have a 2D array with all the coordinates of missing values in the array. This technique turns out to be extremely useful because it allows us to discover the missing values in our dataset efficiently and accurately. Moreover, it can be employed when attempting to respond to other analytical tasks. For instance, with the help of a single iteration, we can fill all these values out. Although it might seem a little wordy, we will use the structure of a very simple for loop. Let's check how it looks. In a new cell, write for array index in. Then paste the argument where and isInAn collaboration before adding a colon at the end. This syntax means we're defining a variable called array index, and in every iteration, we're setting it equal to an element of the arg_where matrix. If you need a reminder of what that looks like, we can examine the output from a few cells ago. It's a 2D matrix, where each row contains a 1D array with exactly 2 values. As we've already discussed, these are the indices for individual elements that satisfy the condition we've set up. Of course, in our case, the condition states that the values are missing. Therefore, throughout every iteration, array index contains the coordinates for a single point, with the row index stored in the first position and the column index in the second. So, on a new line, write out the name of the dataset, and in square brackets, add the expression corresponding to row and column indices for every missing value in the dataset. This means we need to type array index bracket 0 bracket, comma, array index bracket 1 bracket. Then set this equal to some value like 0. This loop should go to each element of the dataset, where we have missing values, and substitute them with the value we set, which is 0. What's next if this works? Then, if we call the line with index 175 again, the missing values should be substituted with zeros. Is this correct? Yes, it is. More precisely, we see that the second and third positions no longer indicate NaN, but zeros. So we've successfully found another way to take care of missing entries in the data. To be absolutely certain we've done everything right, we can double check by calling the isNaN function, plug in lending company data numeric NaN, and call the sum method at the end again. The result is 0, which indicates there are no longer missing values in this dataset. Superb! After mastering argument functions and learning how to sort, we're ready to literally shake things up. In the next lecture, we'll learn about shuffling and examine the different ways we can randomly rearrange ND arrays. Thanks for watching.